Hello and welcome back to Pre-Calculus. We're going to take a look at some concepts from Chapter 10 regarding the sequences and series and summation notation. The first section is talking about sequences and summation notation. So let's take a look. All of this will be very useful for Calculus 2, Calculus 3, differential equations, discrete mathematics. A lot of computer science concepts are rooted in what we are doing here. So it is very, 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 very useful. So we'll start with the definition for a sequence. Now, the book has a very, very lengthy definition for it. Sequence is an ordered list of numbers. That's all we need to know. Sequence is an ordered list of numbers, and I'm going to underline this word ordered. Sequence can be finite or infinite. That's it. So you have a finite sequence and you have infinite sequence. Finite sequence is the one that ends, and the infinite sequence, a list of numbers, it's the one that never ends. So now we can go and take a look at some basic examples of sequence, and then also take a look at the notation and understand what the word ordered means. So sequence as an ordered list of numbers, we're going to say that a(n) can be represented as the set of numbers a0, a1, a2, a3, a4, ... for infinite. Or an could be represented as a0, a1, a2, a3, a4, ... an, finite. So as you can see, the finite sequence ends with some number, where the infinite sequence will go on forever. Now, ordering of an terms is done through the set of natural, also known as counting, numbers. You can also say achieved by, whatever. So there has to be some either formula or recursive formula, we'll see what that means, to generate. There has to be some kind of generator for your sequence. You can't just pile up numbers and call it a sequence. That's a set. It's very loose, right? Definition, set. It's just a bunch of numbers. No order, no rule, nothing. It's just pile of stuff. But the sequence is ordered, and we can come up with a generator that would generate the sequence. Generator is just a formula. So an could be 2n plus 3. So this sequence can have following values. We can say when n is equal to 0 is 3. When n is equal to 1 is 5. When n is equal to 2 is 7. And then you can see that it picks up and it's just all odd numbers. Now it started at 3 because I did plus 3. If I did plus 1, it will start at 1. We start counting at n equals 0 or n equals 1. This is given to you if it's in computer science. Usually they start counting with 0. We know that counting numbers start with 1. You would never go into the forest and start counting trees by saying 0 trees, 1 tree, 2 trees, right? Or if you want to, let's say, if I go and want to see how many students I have in a class, I wouldn't say 0 students and then point my finger and go 1, 2, 3, 4, 5, right? So we don't start counting with 0. But then computer science does, so I mean, yeah. We can have any kind of a function-like formula here, which includes exponents and ln's and literally anything, as long as, right, you have n somewhere to be what we call discrete variable, right, that will take on these counting integer values either from 0 to infinity or from 1 to infinity. So alternating sequence, let's say Bn, is going to be negative 1 to the n, say, times n squared. Why not? As I said, you can literally put anything. It doesn't matter. So if you start counting now at 0 again, zero squared is 0. So the first term is 0. The next term, when n is equal to 1, you get negative 1. And then when n is equal to 2, you are getting positive 4. 3 squared is 9, and the negative, negative 9. So you see that you are getting these squared numbers, but they keep alternating, changing signs, because that's what this does. Negative 1 raised to the n alternates the sign from plus to minus to plus to minus to plus to minus for every term, right? The sign changes. So you end up with every other number being positive and the other number being negative. And this can be as complicated as you want it to be. There are no rules because you can, right, come up with anything. I was looking earlier to see how complicated they want in a pre-calculus course because, you know, calculus 2, discrete math courses that use this. And I ran into an equals negative 1 to the n divided by 3 to the n minus 1. That was in a textbook. So if you want to write out terms, you just have to do it very carefully. Now we see that this one must start at 1 because 3 to the 0 is equal to 1, and then you have 1 minus 1 equals 0 in denominator, and that's not allowed, right? So this particular sequence has to start at 1. Sometimes you will have those that have to start at 2, and because I could have something like this, 3n divided by ln n. You can't start this one at 0. You can't start it at 1 either. So this one you would have to start at 2 because ln of 1 is 0, and that's not allowed to be in denominator. So you have to be a little bit careful where you start your sequence. You saw me start my sequence in the previous two examples at 0 because I can. It's okay, right? We had no problems. But in this case here, starting at 0 is out of question because 3 to the 0 is 1. 1 minus 1 in denominator would be 0, and 0 in denominator not allowed. So when we start at 1, we have negative 1 on top, and on the bottom we have 3 to the 1 is 3, minus 1 is 2. So the first value, first member of the sequence, right, first term of the sequence, is going to be negative 1/2. Then we have a 2. Negative 1 squared is positive 1, so now we have a positive number up there. And then 3 squared is 9, minus 1 is 8. And then we will have negative 1 over 3 cubed 27 minus 1, 26. One more, it's going to be negative 1 to the 4th power. That's going to be positive 1 when you divide, when you put 4th exponent, right? 3 to the 4 is 81, minus 1 is 80. And put 3 dots following the pattern forever. So that one is straight from the textbook. Now, you are able to graph these because they will graph the same way the functions would graph. But instead of having that continuous line for a function, you would have a dot on each integer value. There will be no continuous line connecting all the dots. So y equals e to the x versus an equal e to the n. On the left-hand side, we have our exponential function going through 1, continuous line, x and y inputs. On the other side, we have something completely different. I'm going to draw exponential line, but I'm going to erase it. So don't draw this, or if you have a pen, because you can't get rid of it. If you have a pencil, then maybe you can. So I'm going to draw this just for a second, because I need it to guide where the answer, where the points that I want are. Oops. No, right there. I gotta get rid of these. So I'm just gonna point at them to get rid of them. So at every intersection, I shouldn't be even going negative because we don't use negative. Okay, kill these as well. All right, so now let's delete everything I don't need. There we go. So this is at 0, this is at 1, this is at 2, this is at 3. All you get are your dots, where y equals e to the x has all infinity of the points in between. Let's take a look at another graph, but I'm going to do this one on the same plane. So y equals 2x plus 3 versus an equals 2n plus 3. Oh, and this one I want red. There we go. So now I'm going to draw this function x, y, and at the same time n and an. All right, so 3, 2 units up, 1 unit over, 2 units up, 1 unit over, there, and there. So I'm going to draw the linear line. So the black is the linear line. Black is the function. And now I go red and red and red and red. So you can see they share the same graph, except the sequence can only have dots, and they are not connected. The red dots are not connected with any kind of line because there is nothing in between those values to compute. So it's called discrete. One tick, and then you wait to the next integer, and then another tick, and you wait to the next integer, another tick. There's no 1.5 in between 1 and 2. There's just 1 and then 2. There's no 1.5, there's no 1.7, none of that stuff. And for that matter, we don't even use negative numbers as counters. Sure, we can, because they are integers as well, but no need. So when you have to graph the sequence, think of a graph of the function actually, then draw the same thing, and just leave the points, the red points. Now if I go in and erase the black line, all I would have are just the red points, which is the graph for my sequence. So that's about graphs. Okay, quick recap. Sequence is an ordered list of numbers, and ordering is done through the set of natural numbers, through some kind of formula, pattern, whatever. Sequence can be finite or infinite. Generally, we don't care about finite sequences in mathematics, but computer science, wow. Yes. Or let's say your while loop, right? While the numbers go from your integer counter goes from 0 to 10. Great. Right? That's 11 ticks right there, because 1 through 10 is 10, and then 0, right? 0 tick because it was 0 to 10. There will be 11 ticks. So something will execute, whatever is in the body of the while loop, will execute 11 times. That's straight out sequence that is using to control this. So very powerful concept, and obviously one of the fundamental things, building blocks of any programming and computer science, right, in general. We can generate these sequences easily by continuously plugging in n is 0, n is 1, n is 2. And as I said, in some cases, you cannot have n to be 0 or to be 1 in some cases. And you can easily make situations where other values are taken out as well for your, what do you call it, calculations here. All right. So the next idea is this recursion formula, which I mentioned before. One of the most famous recursion formulas is the Fibonacci sequence, but you can have literally anything else. So for the recursion formulas, we use one or more old members of the sequence, terms, to generate new one. So use one or more old terms in the sequence to generate new term of the same sequence. Now, it doesn't mean a lot to you until you realize which way the Fibonacci sequence works. Fibonacci sequence, also known for Fibonacci numbers, but Fibonacci sequence is a better name. So Fibonacci sequence is 1, 1, 2, 3, 5, 8, 13, 21, 34. I'll put the dots and end it there. It goes forever. Now, please observe that at any point in a sequence, pick any two consecutive numbers. When you add them together, you get the next number. So pick any two consecutive numbers. So let's say you picked 8 and 13. 8 plus 13 is 21, which is the next value. Pick 3 and 5. Next one is 8. 1 and 1. Next one is 2. You can tell me what the next term is. If you pick 21 and 34, next number is 55. So Fibonacci sequence is the most famous of all recursion formulas. And if you are calling these values here, A0 or A1, A2, A3, you can start at 1, or we know that. Eventually, there's going to be AN. Now, the next is AN plus 1. And then the next is AN plus 2. Going on forever. But you can actually, you know what, it will be easier and better if I do this in blood and large. So next would be denoted as AN plus 1. Next is denoted as AN plus 2. But on this side, previous is denoted as AN minus 1. Previous, AN minus 2. So you can use any of these to make the formula for Fibonacci sequence, because no matter which one you pick, take the two before that one and add them up. So if you want your Fibonacci sequence to be defined as AN equals, then take these two and add them up for your formula, and there's your formula for Fibonacci sequence. But can you pick something else? Yeah, you can pick this one and say AN plus 1. That's also a formula for Fibonacci sequence. It doesn't matter which one of these formulas you want to use. They all mean the same thing. Take the two numbers, take two consecutive numbers, add them together to create the next number in a sequence. So it doesn't matter which formula you want to use. That's the recursion. It will be used later, especially in differential equations, for power series solutions to differential equations. So something like this is very, very useful to know. Now, you can make your own recursion equation. Make your own. Literally anything. How about AN plus 1 is 2AN minus AN over 2, just to be annoying, right? Now, you have to be given starting values, because you can't start your recursion if you don't have a point of origin to start working this stuff out. Think about it. if you did not have that an minus 1 is equal to an minus 2 equals to 1, you would not have 1 and 1 to start your sequence. 1 plus 1 is equal to 2. And then 1 plus 2 is equal to 3. 2 plus 3 equals 5. You have to have these. Or over here, an equals to an plus 1 equals to 1 again. So these both are the formulas, but you need these initial values to start off your sequence. So now when you make your own, you have to start somewhere. You have to say A0, your first value, right, is equal to, let's say, 4. So I need this so that I can start. I should have said over here A0 and A1. I know why I did this. A0 and A1. A0 and A1. So those are the first two in a series. You don't have to use n minus 1 because you just need to start it. You don't need for every, right? You just need to start. So just the first and the second number. Just give me those two. And now, why do I need 2 over here and I need only 1 in the example below? Well, if you take a look, over here you have n minus 1 and n minus 2. Those are definitely two different numbers, right? Because when n is 10, if n is 10, then you have A9 plus A8. And A9 and A8 don't have to be the same numbers, right? So we have two different values that are running the show. But in my case over here, I have AN and another AN. That's the same number. So it's enough for me to just have 1 to start off the sequence. So now, what's the sequence? The sequence is, the first number is given, it's 4. And now the second number needs to be computed. Okay, that's going to be 2 times 4 is 8, minus 4 divided by 2 is 2, so the next number is 6. Now 6 is the number that goes into the machine up there. 2 times 6 is 12, minus 6 divided by 2 is 3, so 12 minus 3 is 9. And now we're going to start getting fractions. 2n minus an, so 2 times 9 is 18, minus 9 divided by 2. That's 4.5, so we're getting 13.5. And it's going to go like that forever. But I need something to start. And once I have something to start with, we can go and deal with this. The next concept that we want to learn about before we hit the summation notation is the concept of factorial. So the notation for factorial is n with the exclamation mark, and it's read as n factorial. Right? It's not read as n, it's read as n factorial. There's nothing to be excited about. And the meaning of this is 1 times 2 times 3 times 4 times all of the integer values until you hit n at the end. So what is 5 factorial? It is 1 times 2 times 3 times 4 times 5. That's an example. So 5 factorial is simply multiplying all of the integer values from 1 up to the number that is in the factorial. Now, this will be used a lot. This will be used in Calc 2 a lot as well. And you will see it again in discrete mathematics. Might see it in linear algebra, depending on the concepts you cover. And you will see it in statistics for probability, combinatorics, and so for combinatorics permutations. There are many uses for factorials, and we would like to see, well, these numbers grow very quickly. By the way, 0 factorial is 1, 1 factorial is 1, obviously, and then 2 factorial is 2, and 3 factorial is 6, because it's 1 times 2 times 3. 4 factorial is 24. So you always take the last factorial number and multiply it by the next integer. So 5 factorial is 120, 6 factorial is 720, and then I'm just gonna bail, right? 7 factorial, 8 factorial, 9 factorial. 13 factorial is 6,227,020,800. 10 factorial is 3.6 million. 3.362880. These numbers grow very quickly. 7 factorial is 5,040. 7 factorial is 5,040. So factorials grow extremely quickly, and they are faster than exponential functions. There are not that many things that are faster than exponential. You know from the figure of speech, grows exponentially, right? When someone wants to, even in a figure of speech, people would say that even if they're completely illiterate in mathematics, they might still know that by saying grows exponentially means the values grow quickly. But exponential, the factorial and x to the x grow much faster than the exponential functions. So they're even crazier. Now, which way am I obtaining these values? From 1 factorial, I take the answer and I multiply it by 2 and I get 2. Then I take this 2 and multiply by 3 to get 6. And I take 6 and multiply by 4 to get 24. And then 24 by 5 to get to 120, and so on. That just tells us, and we can also see it from here, that this much is a 4 factorial times 5. Well, that's great. That gives us a formula that n factorial is n times n minus 1 factorial. This is a really cute formula that can save you a lot of calculation in some cases, because you will be able to cancel factorials. And now factorials start playing the role in your sequence. So you might have something like this. Whatever. Let's say an is equal to 2 to the n and then n minus 1 factorial. And you start your n at 1. So you can't start it at 0, because 0 minus 1, it will give you negative 1, and then what's negative 1 factorial? Right? The first definition I gave you is that 0 factorial is 1. So now, when you start writing out your sequence, you have 2 to the 1 over 0 factorial. Then you have 2 squared is 4 over 1 factorial. Then you have 3, 2 cubed is 8 over 2 factorial. And then 2 to the 4, 16. So you just keep doubling the top and raising the bottom by 1. 32 over 4 factorial. dot, 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 going forever. And now you just simplify, make 0 factorial is 1, so that's 2. 1 factorial, that's 4. 8 divided by 2 is another 4. 16 divided by 6, see? This is not 16 divided by 3. It's 16 divided by 2 times 3. 1 times 2 times 3. So 16 divided by 2 times 3, that cancels. So it's 8/3. Now, 32 divided by 4 factorial. 32 divided by 2 times 3 times 4. See, 2 times 4 is 8, so they cancel. You get a 4 on top. It's 4/3 here, going on forever. Not easy to work this back into that, because it's just hard to see these cancellations backwards. But as you can see, you can come up with whatever amount of terms you want or need, depending on a problem, and you can get these values. Just carefully compute one after another. So let me give you one of these calculations to try, and something similar would pop up in your statistics course or something. So let's say you have 11 factorial divided by 3 factorial times 8 factorial. So try to simplify this in some way. I'll give you, if all else fails, just write them out and see what you can cancel. But try it. Any luck? When you compare 11 and 8, you need to peel back down to 8. There's just 3 numbers. And then these guys cancel. And then you can cancel 3 and 9, get a 3 there. Cancel 10 and 2, get a 5. And all you need to do is 11 times 15. 11 times 15 is, you write 15 and 15, so 165. It is fairly simple. Let me see if they have more of these in the homework to simplify. Simplify factorials anywhere. Yes. this thing, 85, is straight out of statistics problem. Now, your calculator is not going to go to do too well if you try to plug. Maybe actually it will. I can't remember. I think 70 factorial is when you get the memory overflow. 70 factorial? I think. When you get memory overflow on those basic TIs. I think. Let me know when you are done. Anyone? Guys, this should really be like 4 seconds of work. 54 factorial divided by 51 factorial times 3 factorial. 54 times 53, keep peeling, 51 factorial, and then 3 factorial is 2 times 3, and then you have your 51 factorial, which will cancel. And now, which ones add to 3 divisible by 3? 54 can be divided by 3 because 5 plus 4 is 9. So those two can cancel. And you get your 3 goes into this once. And then you have 24 goes 8 times. So you have your 18 times 53 times, and then 2 can cancel 52 because they're both even numbers, right? That's going to be 26 over there. So times 26. And there you go. It literally takes a second to do this, which is why we like factorials. They go in. I'm actually going to use the calculator to cheat on this one and multiply everything. 24,804. Where if you are trying to compute those factorials, good luck, because the numbers are astronomical. Well, they're not astronomical, but still large numbers. Last concept that we need to talk about here is this summation notation, which is sum of the sequence. also known as series, sum of the sequence. So sequence is given as an, given as a0, a1, a2, a3, a4, a5, going on forever. And now a series or summation is going to be this Greek letter sigma. That's their capital S. And we are going to have this counter n start at 0, can go to infinity, of an. So this is where you start your counting, and you see that the first term is a0 because n is equal to 0. Then summation means add, and then n ticks to the next number, which is 1, and then the next number, and then the next number, and the next one, going on forever. This is known as infinite series, and just like with your sequences, you can have a formula which generates these terms. And you can also have a finite series. So we can have a finite series. Let's say summation I starts at 0, goes to n of some ai. See, these variables have to match. They have to match because that is where you are stuffing the numbers 0, 1, 2, 3, 4, and so on. So, summation. Say I starts at 3 and goes to 6 of 2i squared is what? Well, the first time around, I is 3. Then it will be 4, then it will be 5, and we have to stop at 6 because the upper limit says stop at 6. So I have 2 times 3 squared plus 2 times 4 squared plus 2 times 5 squared plus 2 times 6 squared, which is 2 times 9 plus 2 times 16 plus 2 times 25 plus 2 times 36, which is 18, plus, actually, better, less calculations, factor out 2, 9 plus 16 plus 25 plus 36, and then just double it. That's much easier. Plus, look at your numbers. 99 and 16, that gives you 25, plus another 25 is 50, so this is 86. So 172. Very, very easy. You have to look at your input number. You have to look at your stop number. Those of you that already know some programming, think of the while loop, right? While loop can be defined more than just from one number to another number. You can have while the number is bigger or smaller than a value and so on. There are many ways in which while loop would work, but one of the features of the while loop easy to use is to go through these integers and have the, let's say, I plus plus, right, to increase the counter within the loop. So it goes, and then you say while the number is less or equal than 6, right, keep running, and then once it hits 6, it stops. So let's see. Actually, I'm going to leave the example here and give you k goes from 3 to 5 of 2 to the k minus 3. So what is this equal to? Try this for a few minutes.
I'm done, Professor.
All right, what do you have? What number?
I got 108.
108. All right. Actually, I'll put it here so I can work it out. So we have 2 raised to the 3 minus 3. That's my first. Plus 2 raised to the 4 minus 3. And the last one, 2 raised to the 5 minus 3. So this would be 8 minus 3 plus 16 minus 3 plus 32 minus 3. These minus 3s are minus 9.
Okay, then I changed my answer.
That's okay.
Totally wrong.
I think
47.
47.
Yeah.
So 8 minus 3, so that will be negative 1 plus 16 plus 32. And yep, 47. You're right, 47. So that will be our summation notation. And really, a lot of interesting stuff is coming up. Let me pick up one more example from homework, and then this section is over. All right, let's take a look at the spicier case. So summation starts at 0, ends at 4. We have negative 1, I plus 1. And then on the bottom we have I plus 1 factorial. This literally has everything we learned pretty much in one problem. All right, try this one. Let's see the way it goes. So make sure you have 5 terms when you start adding them. All right, any luck? Should be done by now. At least close by answer.
Okay, I just did this really quick, but I got the non-fraction version.
Non-frac. What do you mean non-fraction version?
Like I just put into a calculator, so it's not gonna be in a fraction.
Oh, okay. So you got decimals, you mean?
Yeah, yeah.
So what do you have as the non-fraction version, as you would say?
I got negative 1.38 exclamation point.
Like this?
Yes, because I'm not sure what to do with that.
You were supposed to work them out as factorials and then use them in calculation, because this you cannot apply this on a, well, you can, but you can't apply it. You cannot apply it on a decimal. So
That's
we'll
nice.
have to, yeah, we'll have to go and work it out then. So the numbers are 0, 1, 2, 3, and 4. Those are the input values. And for these input values, we have 5 terms that add together. The first one is when I is equal to 0, we have negative 1 raised to the 1 divided by 1 factorial. Then, when it's 1, we have negative 1 squared divided by 1 plus 1 is 2 factorial. And then we have negative 1 cubed over 2 plus 1 is 3 factorial. And then we have negative 1 to the 4th power divided by 4 factorial, and negative 1 to the 5th power divided by 5 factorial. This is equal to negative 1 raised to the 1, that's negative 1, 1 factorial is 1, plus negative 1 squared is positive 1, 2 factorial is 2, plus negative 1 cubed is negative 1, divided by 3 factorial is 6, plus negative 1 raised to the 4th is positive 1, divided by 4 factorial, which is 24. And finally, plus negative 1 divided by 120. So these are our values. And now we just need to add these. So this is actually smaller than 1. It should be smaller than 1. Now, common denominator here is 120. And then we can just go and figure out all of the values. So this is negative 120 on the first, plus 60 on the second, minus 20 on the third, and then plus 5, and then minus 1. Okay, so those are the common denominator. Have 120. What do we have on top? We have negative 60, negative 80. That's negative 80. And then plus 4 is negative 76. Okay. And this is divisible by 4. Okay. So that's divisible by 4. It's negative 19 over 30. Negative 19 over 30. To add up those terms. Negative 19 over 30. And that takes care of the summation notation. Any questions regarding any of the stuff we did so far? I guess no. All right, we'll take a break and then we'll take a look at arithmetic sequence. Bye.